The prevailing belief among most researchers is that the Big Bang Theory remains the leading explanation for the origins of the universe, encompassing the formation of stars, planets, and life, including us. Despite its somewhat whimsical name, the Big Bang Theory provides a clear glimpse into the potential events that may have occurred at the universe's inception. Initially, the universe was compressed into a tiny space, smaller than a pinhead, with particles tightly packed together. From this minuscule point, a massive explosion of matter and energy, known as the Big Bang, occurred. This event, which took place billions of years ago, set the stage for the unfolding of cosmic history. However, advancements in scientific knowledge have led to growing inconsistencies with some of the predictions made by the Big Bang Theory. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space science observatory ever built, scientists hoped that its observations would further validate the Big Bang Theory. Unfortunately, after just 1 year in space, the telescope astonished researchers with its remarkable ability to peer deep into the universe's past. The JWST's extraordinary capabilities have uncovered galaxies dating back to a period so ancient that it challenges our understanding of the universe's origins. This discovery has sparked intense debates about what existed before the Big Bang. One significant breakthrough came when cosmologist Rohan Natu, working with data from the JWST, discovered a galaxy that existed a mere 300 million years after the Big Bang, making it the oldest galaxy ever observed. This finding sent shockwaves through the academic community, highlighting the telescope's immense potential. The JWST's mission to revolutionize our understanding of the universe has only just begun, promising to shed light on the earliest chapters of cosmic history. This largely unexplored era holds the key to understanding the formation of the first stars and galaxies. The JWST's findings have defied initial expectations, revealing galaxies with properties that far exceed previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, prompting researchers to reconcile these observations with existing theories. As scientists grapple with these discoveries, they are confronted with profound questions about the fundamental nature of the universe and the forces that have shaped its evolution. Moreover, the JWST's technology is groundbreaking. Positioned 1.5 million kilometers from Earth, shielded from terrestrial interference, and cooled close to absolute zero by its sunshield the size of a tennis court, the telescope is equipped with a giant segmented mirror and ultra-sensitive instruments designed to uncover details of the cosmic dawn, a period occurring just a few 100 million years after the Big Bang. This epoch marked the time when the first stars and galaxies began to form. The process of how this unfolded remains a topic of intense study, with theories ranging from the influence of dark matter and dark energy to the interactions between starlight, gas, and dust. The telescope's observations of galaxies from the cosmic dawn present an exciting opportunity for astronomers to test their understanding of these underlying phenomena. By studying these ancient galaxies, scientists can either confirm the validity of their current models or identify gaps in knowledge that could lead to groundbreaking discoveries. Initially, it was predicted that the JWST would find only a few faint and small galaxies in its pilot surveys. However, the reality has far exceeded these expectations. The telescope's very first images of the distant universe revealed numerous galaxies with ages, sizes, and brightness levels that surpassed all forecasts. This remarkable wealth of early galaxies has set off a race among astronomers to claim new records for the earliest known galaxies. Every day seems to bring reports of yet another record-breaking discovery, leaving the scientific community in awe and prompting a re-evaluation of our understanding of cosmic history. In the wake of the JWST's findings, both theorists and observers have scrambled to explain the existence of these surprisingly mature early galaxies. Some speculate that errors in the analysis of the telescope's initial observations could be responsible for these anomalous findings. However, the consensus remains that these discoveries represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The JWST's recent discoveries regarding early galaxies raise significant questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists ponder whether these observations can be reconciled with existing theories, others suggest that they may be the first signs that the universe is even more complex and unconventional than previously imagined. At stake is nothing less than our fundamental understanding of how the structured universe we know today emerged from primordial chaos. The JWST's early findings have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant galaxies but also on the very existence of our own Milky Way. As Mark McCaffrian, a senior advisor for science and exploration at the European Space Agency, aptly puts it, "You build these machines not to confirm the paradigm but to break it. You just don't know how it will break." The origins of the JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At the time, Garth Illingworth, then the deputy director of the institute, was tasked with envisioning what would come after Hubble. Despite initial reservations, Illingworth and a small team began laying the groundwork for what would eventually become the next-generation space telescope, later renamed the James Webb Space Telescope after a former NASA administrator. Unlike Hubble, which primarily observes visible light, the JWST was designed to see in the infrared spectrum, allowing it to peer much further into the universe. This capability is crucial for studying early galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST has become the most powerful tool for unlocking the secrets of cosmic dawn. The need for the JWST was underscored in 1995, when the Hubble Deep Field Observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope capable of delving even deeper into cosmic history. After more than 2 decades of development, and at a cost of approximately $10 billion, the JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of scientific observations. Early programs such as the Cosmic Evolution Early Release Science Survey and the Gravitational Lens Amplified Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded them, revealing a universe more dynamic and complex than we had ever imagined. The James Webb Space Telescope, JWST, has surpassed initial expectations, challenging established perceptions of the early universe. Its discoveries are revealing systems that defy conventional models, underscoring the importance of pushing the boundaries of scientific investigation. These unexpected findings highlight the immense potential of cutting-edge technology like the JWST. As scientists continue to unravel the mysteries of the cosmos, they are poised to reshape our understanding of the universe's history and the forces that have shaped it into what we observe today. Early observations from the JWST have astonished astronomers by uncovering incredibly distant galaxies almost immediately after the telescope's deployment. Before JWST, the farthest known galaxy was GN-Z11, discovered in 2015 with a redshift of 11, corresponding to a cosmic era around 400 million years after the Big Bang. However, soon after JWST began its observations, the GLASS team, led by Rohan Natu, and another independent group made a groundbreaking discovery. They identified a galaxy, GLASS Z13, at a redshift of 13, dating approximately 70 million years earlier in cosmic history than GN-Z11. The rapid pace of these discoveries was made possible by simplified methods for estimating redshift, which, although less precise than direct measurements, provide a quick assessment of a galaxy's distance. Remarkably, GLASS Z13 appeared unexpectedly bright and massive, containing a stellar mass equivalent to billions of suns despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings, with many galaxy candidates showing redshifts as high as 20, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited mature structures, a feature not anticipated so early in cosmic history. Additionally, evidence emerged of galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenge predictions of the standard lambda cold dark matter, lambda CDM, cosmological model, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of such size and luminosity should not have formed so early in cosmic history. The emergence of massive galaxies in the early universe presents a significant puzzle for cosmologists. To resolve this dilemma, it is crucial to understand the universe's early stages of development. In the moments after the Big Bang, the universe was a hot, dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of cosmic evolution, from chaotic beginnings to the structured universe we observe today, is thought to have taken about 1 billion years. However, JWST's observations have challenged this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing various small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has detected galaxies that are already sizable and luminous. Further observations using instruments like the Atacama Large Millimeter Array (ALMA) in Chile have provided additional evidence supporting the authenticity of these distant galaxies, ruling out the possibility of lower redshift interlopers. These groundbreaking discoveries open new avenues for understanding the early universe and may require revisions to our current cosmological models. JWST continues to reshape our understanding of cosmic history, challenging assumptions and pushing the limits of astronomical exploration. The absence of detectable dust in the observations made by ALMA emphasizes the challenges faced by telescopes in confirming findings made by the advanced capabilities of JWST. As Rohan Natu noted, while JWST can follow up with its own observations, ALMA's difficulty in detecting the galaxies highlights the complexities of confirming such discoveries. The implications of JWST's observations are profound, potentially challenging the standard Lambda-CDM cosmological model and prompting revisions. Michael Boylan-Culkin and Colin Norman expressed surprise at the findings, suggesting a significant departure from our current understanding of cosmology. One controversial theory that could explain these discoveries is modified Newtonian dynamics, MOND, which challenges the existence of dark matter and proposes alternative explanations for observed gravitational effects. JWST's observations aligning with MOND predictions intrigued proponents like Mark McCaffrian, who saw this as further evidence supporting the theory. However, skepticism remains among scientists like James Bullock, who point out the difficulties in reconciling MOND with existing data. Alternatively, the lack of dust in early galaxies could offer a simpler explanation for their brightness, potentially complicating efforts to accurately measure their masses. Andrea Ferrara suggested that dust may not have had enough time to form in the early universe or may have been expelled during galaxy formation. Charlotte Mason and her colleagues proposed that JWST might simply be detecting the brightest young galaxies, which are easier to observe. David Spergel proposed that efficient high-mass star formation in the early universe could explain the observed brightness of these galaxies. He speculated that early magnetic fields on Earth might have played a role in jump-starting star formation, offering a possible explanation for the rapid growth of galaxies in the early universe. The swift surge of scientific papers stemming from JWST's initial observations highlights the significance of these discoveries and their profound implications for our understanding of cosmology. As scientists continue to analyze JWST data, they may uncover further insights that challenge and expand our comprehension of the universe. When the first data started streaming down from the James Webb Space Telescope, astronomers eagerly awaited the results. Many had spent years developing their data analysis pipelines in preparation. Instead of following the traditional peer review process, which can often take months, astronomers opted to publish their findings on AR14, a platform where scientific papers can be uploaded after minimal review by moderators but before formal peer review. This approach allowed for a new form of peer review to unfold in near real time on platforms like Twitter and other social media channels. Rohan Natu described it as science by surprise, and the ensuing flurry of discussion was intense and unprecedented. Nancy Levinson, the interim director of the Space Telescope Science Institute (STSCI), admitted to underestimating the scale of the activity. However, concerns remain about the potential downsides of this rapid dissemination of findings. Klaus Pontoppidan, the JWST project scientist at STSCI, noted that while the quick sharing of results allows for rapid publicization and discussion, there's a risk of rushing the process.